Welcome back. Today we're going to look at some more horizontal asymptotes. There are some functions that have more than one horizontal asymptote. In the previous examples that we've worked, if there was a limit as x approached positive infinity, the limit as x approached negative infinity was also the same. This occurs whenever we have a rational function. And remember, a rational function is a division of two polynomial functions. However, there are some functions that have more than one asymptote. For example, let's investigate these two limits. The limit as x approaches infinity of 5 plus 2 to the x over 3 minus 2 to the x. And the limit is of the same function as x approaches negative infinity. Well, as x gets larger and larger and larger, 2 to the x is going to get larger and larger and larger. So we're going to have something like 5 plus a very large number. Let's say it's 1,000,000. And then we're going to have 3 minus that very same large number. Let's just use the million as an example. Some value of x is going to make 2 to the x be 1,000,000. So in this case, we would have 1,000,005 divided by negative 999,997. And as we calculate this, this is going to approach -1. So y equals -1 is going to be a horizontal asymptote because the limit as we approached positive infinity was -1. As we approach negative infinity, see the behavior of 2 to the x as x approaches negative infinity. Well, it's going to be the same thing as, for example, if x is -3, we have 2 to the -3rd, or 1 over 2 to the 3rd. So as x becomes a larger and larger negative, the 2 becomes the denominator with a very large power. So as x approaches negative infinity, 2 to the x approaches 1 over infinity, which would be 0. And so basically we're going to have 5 plus 0 over 3 minus 0, 5/3. So we have another horizontal asymptote at y equals 5/3. Take your calculator, put in the function 5 plus 2 to the x over 3 minus 2 to the x, and graph and verify that as we approach positive infinity, we have an asymptote of y equals -1. And as we approach negative infinity, we have an asymptote of y equals 5/3. So a general rule for functions that are divided, not necessarily rational functions, is that if the denominator grows faster than the numerator, the limit as x approaches infinity will be 0. If the numerator grows faster than the denominator, then as x approaches infinity, the limit will not exist. An example, in section 2.1, we learned that the limit as x approaches 0, the sine of x over x is equal to 1. Let's look at the limit as x approaches infinity of the sine of x over x. So with this limit, let's examine the numerator and the denominator. Well, in the numerator, the sine of x is going to fluctuate between +1 and -1 as we go through the various values of x. In the denominator, x is going to keep growing, so the denominator is going to keep getting larger and larger and larger. And so we're going to end up with either a very small positive or negative number over a very big number. And a small number over a very large number is equal to 0. So this would be a case where the denominator grows faster than the numerator. And so our limit would be 0. A second type of limit involving infinity is to determine the behavior of the function as x approaches a certain value when the function increases and decreases. Let's see, up here this is supposed to say x approaches a. Let's investigate the limit of 1 over x as x approaches 0 from the right, and the limit of 1 over x as x approaches 0 from the left. Okay, for 1 over x, when we put in 1, we get 1. When we put in 1/2, 1 divided by a half is 2. When we put in a fourth, 1 divided by 1/4 is 4. When we put in 1/10, 1 divided by 1/10 is 10. When we put 1/100th in, 1 divided by 1/100th is 100. So it looks as x gets closer to 0 from the positive side, the function 1 over x keeps growing and approaches positive infinity. If we look at the other situation, as we're approaching 0 from the left side, x, 1 over x, -1, we get -1. -1/2, we get -2. -1/10, we get -10. And -1/100th gives us -100. So as x approaches 0 from the left, 1 over x is approaching -infinity. And if we look at the graph of this particular function, as we approach 0 from the right, the y values are approaching infinity, so we have that. And we already know the limit as x approaches infinity is going to be 0, because we're going to have 1 over a very large number. And then as we approach 0 from the left, our y values are approaching -infinity. So from the left, our y values are approaching -infinity. And we have this graph that we've seen before, the basic hyperbola 1 over x. So let's define these as vertical asymptotes. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a from the right is equal to either positive or negative infinity, or if we approach that value from the left, we get positive or negative infinity. Notice the word or. That means all we need is one of these two conditions to be met before we can identify it as a vertical asymptote. So this occurs whenever there's a value of x that gives you a 0 denominator, but not necessarily a 0 in the numerator. An important note, infinity is not a number, and thus the limit fails to exist in both of these cases. The expression approaches infinity, but there is no limit. So find the vertical asymptotes of f of x. Describe the behavior of f of x to the left and the right of the asymptote. So if we take the definition above, this is going to occur whenever the value of x creates a 0 denominator. So in this case, we'd be looking at 2x plus 4 equals 0. We're asking ourselves, when does the denominator equal 0? And we know that happens at x equals negative 2. So what we need to do now is to take a look at the function as x approaches negative 2 from the right. And then we also need to look at the function as x approaches negative 2 from the left. Now, a couple ways to do that, of course. Creating a table of values, looking at a graph would be the two that we would probably go with here. So take your graphing calculator and look at the two of these. You should have found that the limit of f of x as x approaches negative 2 from the right is going to be positive infinity. And as we approach negative 2 from the left, it was going to be negative infinity. So to describe the behavior of f of x to the left and to the right of each asymptote, okay, so here to the right, so that would be x approaches 2 from the right, f of x increases without bound. And similarly, as x approaches negative 2 from the left, f of x decreases in value without bound. Here are two other functions. Letter B, f of x equals 1 minus x over 2x squared minus 5x minus 3. Again, we're interested in when is the denominator 0. This is a quadratic, so perhaps it will factor. And in this particular case, it does. Factors into 2x plus 1 times x minus 3. And so our zeros, or the values that create the 0, would be negative 1/2, positive 3. So to establish vertical asymptotes at these particular x values, we need to look at the limit of the function. As x approaches 3 from the right, the limit as x approaches 3 from the left. The limit as x approaches negative 1/2 from the right. And the limit as x approaches negative 1/2 from the left. Again, we can use tables, or we can use the grapher to graph them. Now remember, calculus was developed in the late 1600s. And at that time, they didn't have Texas, so they didn't have Texas Instruments. So they didn't have the calculators that you've got there. So, they had to do some crude arithmetic to get it all done, or they could use a little bit of reasoning here. Okay. For example, let's look at the situation where we're approaching 3 from the right. We're a little bit bigger than 3. If we take that and put it up here, 1 minus something a little bit bigger than 3 is going to be a negative value all the time. So here we're going to have a negative value in the numerator. And it's going to be somewhere close to negative 2. And my numerator is going to be approaching negative 2. In the denominator, if we put in numbers that are close to 3, well, 2x squared, that's x squared is going to get closer to 9. We're going to have 2 times 9, 18. 5 times x is going to get closer to 15. All right? And 18 minus 15 minus 3 is, of course, going to give us 0. But remember, we're using numbers a little bit bigger than 3. So that means this is going to be a little bit bigger than 15. And this is going to be a little bit bigger than 18. Now the question is, which one of these two is actually the larger piece? Because are they both going to be the same amount bigger? Another place to look in trying to determine that denominator is to look here. Choose a number that's bigger than 3, a little bit bigger than 3, like 3.1. 3.1 will make this factor positive. It will make this factor positive. So if we're choosing numbers that are just a little bit bigger than 3, we're going to have a positive divided by a positive. But again, we're getting close to 0. So we're approaching 0 from the positive side. And numbers close to 0 are very small. So negative 2 divided by a very small positive is going to give this to be negative infinity. Let's try looking at this again. Let's use the negative 1/2. X approaches negative 1/2 from the left. All right. In our numerator, 1 minus negative 1/2, we're going to be getting closer to positive 1 and 1/2 here, or 3 over 2. The closer x gets to negative 1/2, the closer 1 minus x gets to 3/2. Now the denominator is where we're approaching 0, so we want to see which side we're approaching 0 from, the positive side or the negative side. So a negative 1/2 in here from the left. So something to the left of negative 1/2. To the left of negative 1/2 would be negative 3/4. And so 2 times negative 3/4 is going to be negative 1.5 plus 1 means this first factor is going to be negative. And then something close to negative 1/2, take away 3 is also going to be negative. If we take a negative times a negative, we're going to have a positive. So that means that we're approaching 0, but from the positive aspect. So again, we're going to be dividing, in this case, by very small positive numbers. And 3/2 divided by very small positive numbers is going to be positive infinity. Get 3 from the left. Again, as we approach 3 from the left, my numerator is going to get closer to negative 2, because 1 minus 3 is going to be negative 2. The denominator is where we're going to be approaching 0. Our goal is to determine which side of 0 we're approaching from, very small positives or very small negatives. And we're approaching 3 from the left, so something like 2.9. When we put 2.9 in here, we're going to have a positive, because 2 times 2.9 plus 1 is going to be positive. When we put 2.9 in here, we're going to have a negative. 2.9 minus 3 is going to be a negative. So a positive times a negative means we're going to have negative values. So we're going to have, maybe we can put the negative out here and call it negative 0. So small numbers that are negative but close to 0. And so negative 2 divided by a very small negative is going to give us positive infinity. With negative 1/2, again the numerator is going to approach positive 3 over 2, because 1 minus negative 1/2 is going to be 3 over 2. Looking at the denominator, we're approaching negative 1/2 from the right, so something like negative 1/4. 2 times negative 1/4 is negative 1/2, plus 1 is positive 1/2. So we have positive here, and negative 1/4 minus 3 is going to be a negative. So we have a positive times a negative. That's going to make our denominator approach 0 from the left. So we're going to have very small negatives. So positive 3/2 divided by very small negative is going to be negative infinity. And in our description of what the behavior is to the left and right of each of the asymptotes, well, our asymptotes are x equals 3 again, and x equals negative 1/2, because we were approaching infinity to the left or to the right of these. So we would describe it either as increasing without bound when we're approaching infinity, and decreasing without bound when we approach negative infinity. Okay, let's go have you do letter C by yourself, and then check your answers with your classmates when you return to class.